Hi guys, it's time now to introduce two different derivative expressions for acceleration for you, which we use when we have a question worded in such a way that the boundary conditions or initial conditions are not expressed in terms of time. Now these might look a little bit weird, but you'll see that they're quite ingenious the way they're derived, and you'll get to really like them. So I'll show you first of all, and then we'll get into some problems and have a look at them. They're really interesting actually. Now, you know, guys, that acceleration has always been written as dv dt because it is the derivative of velocity with respect to time, let's face it. And it's also the second derivative of displacement with respect to time. Okay, that's all done and dusted, and we understand that completely. Now, in this section, two further expressions for acceleration are given using the chain rule. Actually, they're quite marvellous the way they're derived. This is the first one. Acceleration is the derivative of velocity with respect to time. Now, if I, as I say in class, if I chainsaw that off, cut it off, and put the dv there and the dt over there, and I put x as the link, dx is the link, right? Chain ruling it, classic chain ruling it, I can say that that's dv dx times dx dt. That's what dv dt is in terms of a chain rule with a link put in, yeah? Now, dv dx, we just leave that as it is, dv dx over here, and then dx dt, of course, we know that's v. So therefore, look at this, a is v dv dx. I know. And now for my next trick, I'm going to show you the second one, okay? Also, now, look at this. This is really nice. We could write, say we took this expression here, d by dx of a half v squared, right? Now, we're going to chain rule that now. We're going to say, okay, I'm going to chain rule that and put the d of a half v squared dx over here. So there's the top left, there's the bottom right, which was the chainsawed version of what was up here, right? So there's the numerator, there's the denominator over there, and I'm linking that with a dv. See that? With that dv there. Now, so therefore what we've got here, now you have to think about this. What is the derivative with respect to v of a half v squared, right? With respect to v, okay? Yes, basically it is just v. That's what the derivative of a half v squared with respect to v is. It's just v. So it's basically v dv dx, right? v dv dx, and that's equal to a from up here, okay? You see that? It's equal to a from up there. So therefore, d by dx of a half v squared is also equal to a. Okay, another way of saying that would be going backwards from here. We could say, okay, v dv dx is what we know as a, and we could say, but yes, but v is a derivative with respect to v of a half v squared. That's the other way, going backwards. That's actually the way I usually explain it in class. Okay, so look, the two blue boxes are what we want to get out of this. Okay, a is also v dv dx, and it's also d by dx of a half v squared, as well as being dv dt and d2x dt squared. Now, rather than throwing your mind into a fog of confusion, I'll show you how to use when and how to use these two expressions. It's just over the screen, just a moment away. Now, this, what I've written here in this red box here, is absolutely the key to everything here. Now, if guys, you have a as a function of v, it's written as a function of v, function of velocity, and this is the crucial bit here. The crucial bit is the initial conditions are given not in terms of time, but in terms of x and v, right? So if the initial conditions are in terms of x and v, and a is written as a function of velocity, use this one, okay? If the initial conditions are again in terms of x and v, and this time the acceleration is written as a function of x, of displacement, that's when you use this one, okay? And just to add in a third one that isn't written there, just to recap, if the initial conditions are given in terms of time, you use just the traditional derivative expression for a, which is d v dt or d2x dt squared. Now, that's it, guys. That's the bit you've got to remember, okay? If a is this, initial conditions are not in terms of time, use this one. If a is this, initial conditions are not in terms of time, you use this one. Now, let's just put that into practice and I'll show you. An object travels in a line, so that its velocity v meters per second is given by this thing. Now, you can see from that v is a function of x, right? And you're actually not even given any initial conditions here. Find the acceleration when x is 1. Now, you do know, guys, if you think about this, I just showed you over the page that d by dx of a half v squared was equal to the acceleration, right? D by dx of a half v squared. Well, we've got the whole v squared here, not a half of v squared. It's very easy to divide that equation by 2 and get a half v squared, and then to take the derivative with respect to x, because d by dx of a half v squared is acceleration, and we can then just plug in x is 1. So do you see the method in my madness? Yes, I know I'm a bit mad, don't worry. We all are actually, but I'm enjoying myself. So that's all that matters. So we've got here a equals d by dx of a half v squared. Yes, we know that, don't we, guys? So therefore, we can say that a half v squared, as I've just foreshadowed up there, I'm multiplying both sides of that equation by a half, and I get this. Now, all I'm going to do now is take the derivative with respect to x, which is easy to do because this expression is in terms of x, and I've got a. I've got a today. Hooray! Yay! And therefore I've got that. See, look. I just took the derivative with respect to x. I got that. Now I'm going to plug x as 1 in, and Bob's my uncle again. Look at that. Isn't that good? It's absolutely superb. That's what it is. So, yes, I know. It's very, very marvellous. Let's move on now and see whether we can do some more of these things. Now, let's see if we've got some boundary conditions in this one. Yes, it's velocity at the origin. See, no time there. The velocity when x is 0, in other words, is 1 meters per second. So our boundary conditions here are in terms of x. V when, what did I say? Velocity when the origin. So when x is 0, v is 1, right? That's definitely a non-time boundary condition. So we go back to here and we say, acceleration is given by this. Acceleration is in terms of v. So which one did I say to use? If the acceleration was in terms of v, I said to use, go back a couple of screens. If you want to watch pause this and go back a bit, you'll see it was a equals v dx, yeah? And let's see how it works out. Okay, we got that. Yes, and that's that. And there it is, see? There it is. Now, a is v dx. Now, that's the reason that you use v dx is because there's a v here, and if this thing is given in terms of v, it's very easy just to combine all these v's and then integrate if you need to, which we do need to because we're looking for the position, okay, when the velocity is such and such. So, now you know what to do. See, we're off and running now. We've got the right expression for acceleration and all the danger's over. So this is this. You know what to do now. It's a flip, man, isn't it? Mr. Flip. There you go. Now we can integrate that with respect to velocity. And actually we don't even have to make velocity the subject of this because we just have to find the position when the velocity is 2. So that's nice and convenient, isn't it? Now, let's see if you know what to do to integrate that. Do you know what to do? Did I hear you say? Yes, Wolfman. You have to divide the bottom into the top because the degree of the numerator is 1, the degree of the denominator is 1, and the degree of the numerator has to be less than the degree of the denominator before you start integrating with these fractiony ones. Yes, there it is. There it is. Now, you either long divide, or you call that this numerator, when the degree of the top and the bottom are 1, a little trick I showed you a couple of videos ago, you could call that v plus 1 minus 1, couldn't you? Yes, you could, and then you could basically separate it into two separate fractions. The v plus 1 over 1 plus v would be 1, and then this bit is your residual bit from the -1, okay, v plus 1 minus 1. And that's easy, that's very easy to integrate now. This is a loggy one, this is just v. So here we go, let's see. Yes, there it is. V minus log of modulus of 1 plus v. Don't forget those modulus signs, base e plus c. Now, here's our boundary condition time. Come on down, boundary conditions. Velocity at the origin, so when x is 0, v is 1. We better put that in now and see what we get. There we go. Oh, very nice. I'm allowed to remove the modulus signs here because 2 is obviously not less than 0, alright? So therefore c is going to be log of 2 minus 1. And there we go. There it goes. Now, so there's my full expression for displacement. It's this thing minus this thing plus the c term there, which is that. Now, all we have to do now is the final knockout punch. Substitute v is 2, and what do we get? We get that. My goodness, it's pretty involved, isn't it? We could probably clean it up a bit. Certainly we can say that 2 minus 1 is 1, and these loggy terms we can probably combine them into just the log of 2 over 3, I think, just to clean it up. Yes, very, very nice. Okay, how did you go with that? You get it? Hopefully you do. We'll do another one now, just to make sure. We'll probably do a different example of different boundary conditions to use the other expression for A, I think. Okay, off we go. Now, an object is moving in a straight line. The acceleration this time is described by the relation ha in terms of x now, right? So all right, you get the radar up and you say, what are the boundary conditions given in terms of? Where x is a position, blah, 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 yes. Here we are. Given that v is 2 when the particle is at the origin, no problem. See, there's no time there. Look, v is 2 when x is 0. So that's non-time boundary conditions. Therefore, we've got to use one of our funny expressions for acceleration. And so if a is in terms of x, we're going to use d by dx of a half v squared. Okay, that's what you do. It's just a cookbook checklist that you go through. So there we are. There's our derivative expression for acceleration, and it's equal to that. Now we go back to what are we supposed to be doing here? We're supposed to find a relation between v and x. Oh, that's going to be very easy. Very easy. Because we can just integrate with respect to x. Then we'll have to take a square root somewhere along the line here to get v, because this is half v squared. And then just be very careful that we haven't introduced spurious solutions, because when you're square rooting something, you better be careful, because one of the solutions is likely to be wrong. So we check it against our boundary conditions, as I have mentioned in previous videos. So, alright, I integrated that. Now, do you get that? That's x to the half. 1 more than a half is 3 over 2, so it's minus 1 over 3 on 2, which happens to be 2/3, x to the 3 on 2 plus c. Now we better put our boundary conditions in now, and there it goes. When v is 2, x is 0, and we work out that c looks like it's 2. Okay, so now half v squared is equal to all that. That's very nice. Now we've got to solve it for v, don't we? We've got to come up with a relation between v and x, which describes the motion, right? And let's do that. Okay, I've doubled, multiplied both sides by 2. Now I've got to take the square root now. Yes, but as I said, it's time to be very careful, because one of these is likely to be an imposter. So we go back and we'll check our answer, because we know that when x was 0, v would be plus or minus 2 according to this. But according to that, when x was 0, v was plus 2, right? So plus 2 means we're going to get rid of this negative solution. We have to reject it, okay? We have to reject it. Yes, and we get that. Now, is that the end? Is the end our friend? I think it is. Mr. Box. Thank you, Mr. Box. Jolly good job, Mr. Box. So we'll move over now and we'll do another one. An object falls from a hovering helicopter, I hope it wasn't a person, over the ocean 1,000 metres above sea level. Find the velocity of the object when it hits the water, A, neglecting air resistance, and B, assuming air resistance is 0.2 v squared. Well, ladies and gentlemen, this is actually a fascinating question. Why don't you pause the video now and have a go at that, and we can come back when you're ready, okay? Okay, how did you go? The reason this is so fascinating to me is that there's two completely different approaches necessary for part A and part B. Because if you neglect air resistance, then all you're dealing with is the acceleration due to gravity, which is 9.8 meters per second towards the center of the Earth, right? Which is a constant acceleration. Badumch, did you get that? A constant acceleration, which then we can use our license to drive with the constant acceleration formulae, okay? Whereas this beastie here, he's not constant at all. In fact, you've got the acceleration due to gravity pulling him down, but you've got this variable acceleration dragging him and slowing him down, or if you like, pulling him upwards, okay? So that one's, you can't. There's no license to drive there with constant acceleration. You've got to do that one with the traditional integration approach, okay? So let's do it and see how we go. There's A today. Now, what I did, well, that was probably not the best choice because this thing's moving down. But I did choose, I'm just used to choosing up as my positive direction, okay? And we're all creatures of habit, so that's what I just normally do. So therefore I've said that that A is minus 9.8 meters per second squared, okay? It's minus because it's down and my up is positive. I know that my initial velocity is 0 and I want to know what my final velocity is, and I know that x is minus 1000, okay? So which formula would you use? What formula would you use today to work that out? Yeah, I think that's a v squared equals u squared plus 2ax, don't you? Because we don't need time. We're not asked for time. And we just plug and play. There we go. So v squared is our final velocity. U is our initial velocity. And we've got, now, oh yes, I put a minus there because a is minus. And x is also minus. So look at that. See? Got to be very careful with the signs of these things, and I'm getting v squared is that, and therefore it looks like it's, wowee, that's mighty fast, guys. That is mighty fast. Minus 140 meters per second, because it's going to make an almighty splash when it hits the drink. Yes? Now let's do part B. Actually, part B, the result is extremely different. So, yes, I'm assuming here, because they said here the air resistance, that's very badly worded, even if I do say so myself, no offence to anyone, very badly worded, because that's air resistance is a force. So I assume they're saying acceleration there when they say that, so let's just assume that's what they mean. Now, A in this case is minus 9.8 plus a half v squared, because that's a down and that's an up in terms of direction, all right? Now, what are we got to do? We've got to get the final velocity, don't we? So we know that v is 0 when x is 0 in our frame of reference. So what we've got to do now is anti-diff this to get the velocity, right? Now, this one here, do you note the boundary conditions? I'm saying v is 0 when x is 0. So therefore, what derivative expression are we going to use for acceleration, guys? Okay, this is in terms of v. That's my hint. That's my hint to you. That's in terms of v, right? Non-time boundary conditions. So, what have we got? We've got that, okay? That's the one. v dx equals that, yeah? So now we better get this v out of here and over there to join the other v and keep it company. And we've got, and I've made a bit of a simplification throughout the nation there. It looks like that. So if you multiply that by 5, you get 49. Minus 49 plus v squared over 5 equals v, yeah, now I've still got to divide by v, don't I? Yeah, that's it. Now I've divided by v, both sides. Okay, now I've got to flip. This is a flip, man, because you can't integrate with respect to x, because this is in terms of v, as you well know. Okay, there we've got that. Now we're ready. We're ready, guys, to integrate. Woo, look at that. So now what have I done? Slow down, Wolfman. You've got this. That's all right. But now what I've done there is I've got an original function plus its derivative present within the integrand, but the derivative is 2v, not 5v. So I took the 5 out there to get it out of the way, and then I put a 2 in there, and then I divided by 2 to compensate. You see, aren't I a crafty devil? So there it is. Look, I've got it exactly where I want it now. So that's going to be log of this, with modulus signs on it, of course. So there it goes, yeah? 5 over 2 log of that plus c, right? Now leave those modulus signs on there until we know what is going on, guys. Do not put brackets there. That is a very dangerous and wrong thing to do until you know what's going on. Now we put our boundary conditions in, and what do we get? Yes, that's obvious. X is 0 when v is 0 in my frame of reference. Now, let's put that in. We get this expression, don't we? Is that right? Yeah, because v is 0. Therefore, the modulus of minus 49 is just 49. Don't need the modulus signs for that because 49 is not negative. Now, therefore, c is that, all right? Now, therefore, I've got this. Now, I've just put it in a more convenient expression, right? So I've got it, instead of this thing and then the c thing happening after there is minus 5 over 2 log of 49, I've put it as the 5 over 2 log of this over that, according to our log laws now. Now, get ready for the pea and thimble, the Wolfman pea and thimble trick. What I've done there is I've multiplied both sides by 2 over 5 to get rid of that 5 over 2 there. I get that. Now, this is the pea and thimble trick. Look, I've said, okay, this thing without the modulus sign, is equal to some constant, just some constant, times e to the 2x over 5, right? Now I'm going to work out the constant which will take care of whether this has got to be a plus or a minus or whatever's going on here. Okay, so we'll put in our boundary conditions. Yes, now you watch this, See now, if v is 0, right, if v is 0, that becomes minus 1, doesn't it? Minus 1. If x is 0, that becomes 1, and therefore you're saying that minus 1 equals a. See? It's so easy when you do it that way. Now, so therefore, where are we now? We've got this is equal to that, right? So now what we've got to do is make v the subject, and then finally, what are we supposed to do when the object hits the water? Yeah, so make v the subject first, then we'll put in x is minus 1000, and we'll have our answer. Okay, so v squared is that, isn't it? Yes, v squared is that. Now we better do the square root, but then watch very carefully with the result. One of them is going to be wrong for sure. In fact, you know, I don't even need to plug any boundary conditions in here, because actually, if I plug in a boundary condition when v is 0, x is 0, it won't make any difference. It won't distinguish between these two possibilities. Okay? Because I'm going to get, yes, I'm just going to get v is 0 when x is 0. So that doesn't help me with the plus or minus, you see. But then you can say to yourself, well, wait a minute, v is always going down because that's my frame of reference, see? Up is positive, v is always going down, so v has to be negative. It's not going to go and turn around and go flying up through the sky. It just doesn't happen with gravity, guys. So that's what we're going to say. And we've worked it out just from logic. V must always be negative because up was taken to be positive at the start of the problem and the object is moving downwards, yes? So that's what V is, okay? Just from logic. Now, our final knockout punch, and we put in x is minus 1000, and what do we get? And there she be, Jim. There's the answer. Thank you, Mr. Box. That's basically with minus 1000 put in there. 2/5 of minus 1000 is minus 400. Now, that would be such an infinitesimally low number. To all intents and purposes, it would just be minus 7 metres per second. Minus 7 metres per second. Now, that's the exact answer, of course, but you know, that's what I understand the answer to be, as good as, you know, minus 7 metres per second, but I quote the answer as that. But the point I wanted to make to you is that isn't that an incredibly different result from what I got from neglecting the air resistance, which, if I remember, was 140 metres per second. My goodness! So in this case, air resistance has slowed the thing right down to what we call a terminal velocity, if you like, as good as terminal velocity of -7 meters per second, which is considerably slower. Considerably slower. It's just over 20 odd kilometers per hour, I think. So that, you know, if a human being happened to hit the water at that kind of speed, well, it's conceivable they might survive, but certainly not at 140 metres per second. How interesting, eh? All right, I think that's the end, and the end is your friend, of course. Yes, that's what I've said there. It's good as. Yeah, that's a very good job. A good job for you and a good job for me. Let's pat ourselves on the back and go and do some practice, and I will see you in the next exciting instalment.